Hi everyone. In this video, I'd like to give you a graphical intuition into the process behind hypothesis testing. So we went through a simple example where the way we figured whether we should reject a null or not is we're trying to figure out how to label something to be an extremely unlikely event. In the context that when we assume the null to be true, if we see an extremely unlikely event, then that is evidence to believe that the null is actually false. Now, we labeled these unlikely events by setting a threshold level of probability and comparing the likelihood of these events to that threshold. Now, stay with that example, and we'll see how that graphically plays out. And once you understand this graphical intuition, the steps of hypothesis testing will follow very intuitively. And the magic here is that you only require two important elements to understand this: the central limit theorem and the empirical rule. So let's see how this works out. So let's take, for example, we're testing a hypothesis about the population mean, and we're going to hypothesize that it is going to equal some value mu naught. Mu naught could be any number. I'm just going to refer to it as mu naught. And I'm going to look at the alternative that mu is not equal to mu naught. Now, if this is a hypothesis about the population, then how do we look for information in our sample to see whether our sample is giving us reason to believe that the hypothesis null is true or whether we should negate the null? A reasonable starting point is to look at x bar, because x bar is the sample counterpart of mu. If x bar is reasonably close to mu naught, we may want to conclude that the null is probably true. If x bar is quite far away from mu naught, then maybe from the sample there's no information to suggest that the null is true. And that's a fair enough starting point, so we'll stick to that logic. Now, the problem here is that x bar is just one single number, and it has come from one specific sample. Maybe if we look at a different sample, we may get a different x bar, and how close or far away from mu naught that x bar is, our decisions may change. So to get around this problem, suppose we decide to take 20 different samples. And suppose we find out that in 19 out of those 20 samples, x bar is very close to mu naught. Now we've looked at different samples, and we know that from, even if there is variation in sampling, if we account for it, in 19 out of 20 cases, our x bar seems to be close to mu naught. So we have enough information to believe that the null is true. Similarly, if you find the result to be otherwise, suppose in 19 out of 20 samples, you see that x bar is quite far away from mu naught. So none of, a majority of your samples are telling you that from the sample, there's no information to conclude that the null is true. Therefore, we must reject it. In either cases, just by virtue of having more samples, we're able to make a stronger statement about whether we are believing the null or rejecting the null. All of this is fair when we are able to compute 20 different samples or 30 different samples, but we don't have that luxury. We only have one sample and a single average number from that. So from this single number, how do you make statements about rejecting or not rejecting the null? This is where the central limit theorem comes in very handy, because it tells us that the sampling distribution of the sample mean x bar follows a normal distribution with the same mean as the population and a variance of sigma squared by n. Now, if I were to believe the null, if I were to believe that the true population mean is indeed mu naught, central limit theorem will tell me that x bar should also have the same mean mu naught. This is under the case that null hypothesis is true, when we believe the null to be true. Now, the advantage of bringing in the central limit theorem here is that we can have a distributional function to describe the probability of x bar values. In other words, let me just give me a second, let me redraw this chart. So from the central limit theorem, I know that my distribution of x bar values looks like that, and it is centered around mu naught. Now, why is this shape advantageous? It is advantageous because given that I know how the sampling distribution of x bar looks, even without computing it from different samples, I know the general shape of the distribution, and because of that, depending on whatever x bar value I'm actually getting in my sample, I can compute the likelihood of getting a number like that. In other words, suppose my x bar is a number here, okay? Suppose my mu naught is 10 and my x bar happens to be 12. My x bar will be somewhere here. And I know that given the sampling distribution of x bar, there's a very low likelihood of getting that number. On the other hand, if I get an x bar that is somewhere here, then I know that there's a very high chance of getting a number like that. Now, what this allows me to do is that because I know the probability distribution of x bar, I can check if the particular sample value that I'm getting is a number that is highly likely to show up or highly unlikely to show up, purely by looking at the shape of this distribution. And once I'm able to figure out if some number is likely or unlikely, I can then proceed to check if it is unlikely relative to a certain threshold that I can set. And this is where the beauty of central limit theorem plays out in hypothesis testing. So how do I go about labeling unlikely and likely events? And now we can use our empirical rule. So if I have a normal distribution for x bar, and if I have a mu naught, I know that within one standard deviation, I have 68% of the cases. Within two standard deviations, I have 95% of the cases. And within three standard deviations from the mean, I have 99.7% of the cases. Now, if I decide to set an alpha level of 5%, then I'm effectively saying that, I know that within two standard deviations from the mean, about 95% of the data is covered. So the rest of the 5% goes into the tail. So there's a 2.5% probability on this tail. There's a 2.5% probability on the left tail. Now, if I end up observing an x bar value that falls into either of these tails, I know that there's only a 5% chance I could ever observe a number in these extremes. And it's either 5% or lower, depending on where exactly it falls along the x-axis. And because I'm now able to explicitly identify the region where I can check, the region which is beyond my threshold. I mean, if I take alpha to be my threshold value, any event that has a 5% or lower probability is unlikely. And I know I've been able to identify those regions by demarcating these cutoff points. And once I know that a specific x bar value falls in either of these regions, I can use that as evidence to reject my null. In other words, I can use it as evidence to say that x bar is very far from mu naught and therefore reject null. So this is the principle behind how hypothesis testing works. We use the central limit theorem and then we use the empirical rule to demarcate the regions where we are willing to believe the null and the regions where we are going to reject the null. Now here I've showed you an example where the 5% area is split in the two tails, where because my the null was mu is equal to mu naught, and the alternative was that mu cannot be equal to mu naught, and therefore we could look at both the tails. The 5% probability can be split. The actual x bar mu can be greater than mu naught. It could also be lesser than mu naught. So I'm allowing for that flexibility and I'm looking at both the tails, and this is called a two-tailed hypothesis test. Using the same logic, I could also look at cases where I'm testing mu is equal to mu naught versus mu is lesser than mu naught, or I could look at cases where the alternative is one-sided but in the other way. So how will this look graphically? So if I have an x bar distribution and if I have mu naught, let me just draw this diagram again so that we could see the other case. Now, if I'm looking at mu lesser than mu naught, I'm going to be focusing on this region because that's where my mu could be lesser than mu naught. And if I set a same threshold of 5%, I'm going to be looking at cases of finding extreme values such that those extreme values have a less than 5% probability of showing up. Now, because my interest is only in this region, I'll choose a cutoff threshold here such that this area is equal to 5%. And any observation that falls in this space has either a 5% or lesser likelihood of showing up, and that will be my unlikely event. So the way I define my null and alternative will figure out what my, the specific area which will determine whether I should reject the null or not. Similarly, if you take the other hypothesis where mu is greater than mu naught, I'll be focusing on this part of the distribution. And if I set a same threshold alpha of 5%, I'll look for unlikely events such that there's a 5% chance or less of seeing that an observation like that. And therefore, I'll set a cutoff here in such a way that this area is equal to 5%. And if I see any value in this area, that will lead me to reject the null. So this is the general principle behind hypothesis testing. In this case, where you looked at both tails, it's called a two-tailed hypothesis test. Here, it's a one-tailed hypothesis test, but the intuition is the same. And depending on what alpha value you choose, the area of rejection may become smaller or larger. So when you choose alpha to be 10%, your area of rejection will be bigger. If alpha is 1%, your area of rejection will be smaller. So this is the key intuition behind how the graphical process works, how we are able to identify and label and identify the unlikely regions. Now, there's one more thing that I'd like you to learn. When you learn about hypothesis testing, you will come across something called a z-stat or a critical value. Okay, you will come across something called a critical value. Let me not call it z-stat. So critical value is actually nothing but these thresholds that you're setting. Thresholds, okay? And oftentimes those thresholds will either be referred to as either z or t, okay? And z will be written down as x bar minus mu naught by sigma by root n. Sometimes you'll have another expression called x bar minus mu naught by s by root n. Now, why am I depicting these critical values using complicated expressions like these when I've only been showing you graphs that have x bar and mu naught? Where is all this coming from? Well, it's very simple. We know that whenever you have a normal distribution like this, I could always convert it in such a way, I could redefine the random variable in such a way that the redefined random variable follows a standard normal distribution. And what do? When I convert every single observation to its corresponding z-score, and I look at the column of all of those z-score values, I end up getting my random variable is effectively transformed to be like this, right? You subtract the mean and divide by the standard deviation. And this will end up following the standard normal distribution. Now, all I have to do is just say that let z be defined as x bar minus mu naught by sigma by root n. And once I define it this way, what happens is that this and saying that z follows the standard normal distribution, these become equivalent. And when they become equivalent, comparing x bar with mu naught is equivalent to comparing z with its mean 0. And how does this look visually? If this is my x bar centered around mu naught, my transformed variable will be z, and it will be centered around 0. And the same empirical rule applies, but life will become much easier now. Because instead of one standard deviation, I can just count the number of z-scores away from 0. Because z-score essentially is the number of standard deviations above or below the mean, away from the mean essentially. And once all of my random variables are defined in terms of z-scores, the z-score itself will give me how many standard deviations away they are. So a z-score of 1 and minus 1 will encompass 68% of the data. A z-score of -2 and +2 will encompass about approximately 95%. Between -3 and +3 will end up having 99.7%. And we know from our examples in class that it's very easy to identify these threshold values when you're dealing with the standard normal distribution. We can either look at the table or we can use computer or an applet to figure out these z-score values such that the area to the left or to the right is a certain specific number. It's much easier to compute those areas using the z-score value. So once I identify those cutoff points, these critical values, so these critical values are therefore denoted using this expression because they come from the z-score table. And I mean, this specific expression that you see here is the specific z-score value for our sample x bar. And we'll compare that specific z-score value for our sample x bar, and we'll compare that with these cutoff values that I evaluate from the normal distribution, the standard normal distribution. If I find that my x bar minus mu naught by sigma by root 10 happens to be in this threshold or somewhere in this threshold, then I'll go ahead and reject the null hypothesis. So it's essentially saying that if my x bar is above, if the x bar that I find is above the specific threshold that we're seeing here, then that would lead me to conclude that the null is false. So it's the same reasoning, except that I've transformed my x bar variable into a z-score variable. And that's why you will see this expression showing up. Now, when we know sigma, we can use the standard normal distribution. But when we don't know sigma, we'll often end up using S to approximate it. And that will follow a T distribution with n-1 degrees of freedom, where n is given by the sample size. And the T distribution has identical properties as the normal distribution. It is symmetric, and and these are actually called T-stats or T-scores. And the T-scores tell you how many standard deviations away from the mean you are in a T distribution. So essentially the interpretation is the same, except that instead of looking at a Z table, you look at the T table, but every other interpretation remains the same. So we'll compute this T statistic, and we'll also compute these, corresponding cutoff values. So this T statistic I'm mentioning is specifically converting your sample X bar to its corresponding T score or Z score, depending on whether sigma is known or unknown. And you'll compare that score with these threshold values, which you will just determine from the tables based on whatever you want the areas to the right or left to. And once you make, when you make these comparisons, keeping a certain threshold value in mind, we can go ahead and say whether we are rejecting the null or not rejecting the null. This is the principle behind the graphical intuition. So now we'll learn about the steps involved in hypothesis testing. So let's see in that video.